you kick out an electron. So here's how they knew this was even happening. What they would do is they would take a large sample of carbon-14, which is a radioactive version of it. Again, you have to go through the separation process. And what they would notice is that over a period of time, nitrogen would begin to show up. I think like 2,500 years, and I may be way off on that. So what they would notice is that even though there was no chemical reaction taking place, they would begin to see elements of nitrogen within the sample. I was like, how can you get nitrogen in here if all you have is carbon? And that's what they began to see. It's like, oh, this is what's happening. So this is the dichotomy. Is that beta minus, you add an atomic number of 1 in beta minus. So beta minus, you add a proton. Okay? Now, in contrast to that, you can have beta plus. Okay?
What's that do?
Yes. So you could have magnesium turning into, in this case, sodium. And you kick out a positron. Positron is an electron in every way, shape, or form. Same mass, exact same characteristics. The only difference is that it has a positive charge.
Well, why is it a positron, Barry?
Because that's the only way you can balance out the charge. Now, here's what's common to these. Just hold on a second. So here's what's common to these. In both of these, notice that the mass numbers stay the same.
Yeah.
Okay? So what's happening here is just the opposite. Here you're taking a proton, and you're taking a proton and turning it into a neutron. Okay?
I think it's
Wow.
I love how it just like it
just randomly.
it was like at the perfect time.
So
choose a proton, choose a neutron.
yes, like all of a sudden music. Oh, cool. So here's what happens in beta plus decay. This is again the dichotomy. So beta minus, you add a proton. In beta plus, you subtract a proton. Okay? So here's what's happening. Inside the nucleus, you're taking a proton and you're turning it into a neutron. So here's one of your guiding lights about this whole thing. What determines, the only thing that determines the element to which any atom will belong.
I think
the number
neutrons.
of protons. It is not the number of electrons. It is not the number of neutrons. It is solely the number of protons. So here's what happens. This is why you have to kick out a positron. Because what's happening is you're taking a proton, so you're decreasing the number of positive charges. So to account for that, you kick out a positive charge so that everything remains in balance. Check.
Why doesn't the positron just go out and then smash it through an electron?
That's what's going to happen.
Kaboom.
That's the mixed up. So electrons and positrons, as soon as they run into each other, annihilate each other. That was the whole point of, yes, Alyssa.
Where did the positron come from?
So the positron, that's when you get into what's called quark theory. Okay? So what happens, quarks are weird because they make up, you have up quarks and down quarks and all this other stuff. So what happens is that to make this transition from the proton into that neutron, to do that, this is where the positron comes from, and that has to do with the interaction of the quarks. Don't worry about it. Okay? That's what happens. Yes. At this point, just accept it. Yes.
Okay, so since protons, like, are the element, right? Like, it makes up what the element is. I forgot, right?
Yes.
So technically,
atomic
could there be an infinite types of atoms out there?
What?
The problem you run into is that you're trying to build a tower out of jello. So you could, in theory, build a tower of jello like a mile high, but it becomes so incredibly unstable.
Oh.
Yeah, so this is why even like when you complete the periodic table and you get into those big, heavy ones, we can only produce them in labs, and they have typically occur for a very short
Because
amount
they're
of
so
time.
unstable, they can't hold themselves together.
Exactly. So you can build them, but they're artificial because they immediately decay because of the fact that they're so unstable. Thank you. Okay. So again, all you have to do is make the math add up. Now, this is something that Shaq alluded to. The problem with creating a positron is that as soon as a positron runs into an electron, they annihilate each other and they change back into energy. But the amount of energy that you get, which is quite large, is mc squared.
No way.
So, if you know, and you can do this, so what is, in rough numbers,
3 times 10 to the 8.
what's the mass of an electron?
9/11 to the negative
31.
9.1, so let's do this.
Negative 31.
So take 9.11 times 10 to the negative third. That's the mass of either an electron or a positron, it's the same thing. So, we're going to multiply that by 2,
Why?
because a proton and a positron are going to annihilate each other.
At the speed of light?
Yeah, it really doesn't matter how fast they go.
Oh, yeah.
But then we're going to multiply that by 3.0 times 10 to the 8th meters per second squared. So this is from Einstein's relativity. So anytime a proton and an electron, excuse me, a positron and an electron run into each other, they instantly annihilate each other and they change back into pure energy. So what do you get out of this then? Well, that's like 10 to the 16th. That's 9 times 10 to the 16th.
Is it like 0?
It's a small number.
Bro.
1.64 times 10 to the what? Negative 13.
Check how confident.
That's
Okay.
not a small bird.
But now, here's the cool thing about this, and this is how we make positrons,
Positrons.
is that this door swings both ways. If you have a proton, excuse me, a positron and an electron, and they run into each other, this is the amount of energy that you create. If you have this much energy, then you can make the door swing the other way. Then, if you have that much energy, then you can make a proton, excuse me, a positron and an electron appear out of this. Now,
What?
if you were to do this with a proton, what would happen to the amount of energy?
More energy.
This is the story from the bank.
More mass, man.
So if you want to make, this is the story of the bank. They created the electron and the positron. Okay? They created the electron and the positron. That required a certain amount of energy. But they were short-lived. Because why? They're going to annihilate each other. So they can live fast. Great. Okay? But they're going to run into each other and they're going to switch back into pure energy. So if you want to make a proton and a negatively charged proton, that's a lot more mass, which is going to require what?
More energy.
That's
A
why they
lot
really
more
exist.
energy.
Wait,
Okay.
can I get a proton thing?
Oh yeah.
What?
But
Wait,
it
what?
requires so much more energy because they have so much more mass. Now, this is why it's very easy to produce photons. Photons don't have rest mass. They just have energy. So this is why when you turn on the light, this is why it streams photons and not electrons. Because to produce an electron out of light
What energy?
would take a lot of energy.
Not efficient.
Alyssa,
So where, okay, so does a neutron weighs more than a proton, right?
it's tiny, 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 tiny. And that's part of what that positron or electron comes out of, is that difference in mass.
The difference in mass is
Yes.
the positron?
It's actually one of the quarks. It's like an can't remember if it's an up quark or a down quark. It's one of the quarks.
So in
That's the
neutron,
difference.
a neutron is a proton that is a positron?
Basically, so there's different quarks that make up protons and neutrons. And I don't remember, there's like quarks have charge, like either 2/3 or
What?
1/3.
You
Okay?
can't do that.
And there's 3 quarks that make up either a proton or a neutron. And so if you have the right combination of quarks, then you get a positive charge. If you get the different combination of quarks, then the charges balance each other out, and then you get a neutron.
Very.
So
Let me figure this
if
I
Nathan,
think it's
Yes.
Google, what quarks make up a proton?
What quark
Quarks.
make
Quarks.
up a
How do you spell that?
Q-U-A-R-K-S?
A-R-K-S.
Proton composite. Wait, what? Oh, it's made up of 2 up and 1 down.
Yeah. So
Held together by gluon.
What do you mean
Yes.
up and down?
So you have 2 ups, and so protons are 2 ups and 1 down.
Yeah.
So ask it what neutrons are made of.
It's definitely 2 down and 1 up.
Yeah,
What are neutrons made of?
neutron
So the
quarks.
downs weigh
Oh.
more than ups.
What are you asking?
Neutrons
So
are
ask
made of what?
the same
Neutrons are made
question
of.
about neutrons.
Oh, I got you.
Bro.
Is that gonna be on the test?
3,
Oh,
wait,
good
1 up
question,
and 2 down.
1 up and
2 down.
2
Do we
down.
need to know
What about
this?
electrons?
Now ask. No, this is not going to be on the test.
For electron?
Okay.
So ask what charge is on an up quark.
What
What?
charge is on?
So does a down weigh more? Does it?
No, it has to do
What is
with
that? What
charge.
is that up down?
Oh.
even? I'm
1/6 to the negative 19. Wait,
No,
what?
no. On the
That's the
quark.
charge.
An electric
2/3 of an electron.
Yes. So this is where the fraction of charge comes into it. Okay? So
Can I learn this card?
color charge?
only if you study what's called the standard model.
Bird, can we see quarks?
No. We can't even see the electron. So the only reason that we knew quarks even existed is because we smashed protons together with a high enough energy source.
But then how do we
Okay.
know that they exist?
What do you mean?
Like you said,
Because we detected them in cloud chambers. That's how we
Are they
know.
like really that tiny?
Hey, we recorded video.
Okay. Now, next thing you can get into is what's called a
Gamma?
production of neutrinos.
Neutrinos?
Okay, now, neutrinos are incredibly weird. Okay?
Sorry.
So, right now, literally, like if you hold up your thumb, every second that goes by, there are literally millions of neutrinos that are streaming through your body.
What?
They don't interact with anything, they just go through them. One of the great mysteries is that why neutrinos even exist.
How do we know they exist, Bird?
We've detected them. That's how
Oh
we
yeah,
know
my
that
fault,
they
my
exist.
fault.
Okay.
What is your
I'm
fault?
sorry.
We just don't randomly make up stuff.
You
Okay?
Are we sure?
To a certain extent.
I feel like it's made up though.
So,
Where's the proof?
there are millions upon millions of neutrinos streaming through your body. Conveniently, they don't interact with anything. Okay? And neutrinos are weird. There's like 3 different types of neutrinos based upon how long they live once they're emitted. Neutrinos are a whole other story. Now, you can also have what we call gamma decay.
Wait, what's the point of neutrinos?
No one really knows.
Wait, are they like the smallest thing all time?
No, quarks.
What's smaller than quarks?
Yeah, we probably don't know about
That's
Well,
what the
so,
smallest-
There could be.
When you get gamma decay, the beauty of gamma decay is it's a very high energy photon. It does not alter the atomic number. It just kicks out an extremely high energy photon, and that makes the nucleus more stable. So, Louise,
Never mind. I'll ask you later.
How do we know they exist?
Yeah. How do we know that happened?
Okay.
It's all theoretical.
So,
It's not a-
the beauty of gamma decay is you don't have to do any math.
Let's
Okay?
go.
If you're told something goes through gamma decay, it just kicks out an extremely high energy photon. Conveniently, that doesn't happen very often because gamma rays, we call them rays, they're just photons. If they interact with your DNA, it tends to wreck your DNA.
Oh, we die?
Bad things happen.
So did
Well,
Chernobyl
you
have
don't die,
gamma
but if you
radiation?
have a high enough gamma ray exposure, it can.
Were Chernobyl's gamma
die.
radiation?
Now,
Lose a part of
just
your DNA.
hold on.
Oh, we should watch Chernobyl.
Okay.
Bad.
Yeah.
So the
Very
next
bad.
thing you can have is something called electron capture. This doesn't happen very often.
Got one right here.
You're back.
I can't. You know what I'm
Wait, you take
Why do you have to
Is that 81?
high energy
Nathan, you know what I'm
No,
talking
gamma
about?
decay is just
You know the
like super
That's
high
fine.
energy.
Nathan, just
What
play
is it
escape
from?
time.
Those are photons.
No, it's from the two guys.
Hey, Adam, up your screen time.
Did you
buddy.
learn this in
Yeah.
college?
Up your screen
Yeah.
time, Bob.
You're alarming, bro. You're alarming heavily.
Yeah. Let me guys get
Okay, so
Mark,
I
he was
have-
What Hobby Lobby does.
So,
Hey, Nathan, we're large.
That
right?
neutrino?
rare that this happens, you can have something called what's known as an electron capture. So, here's what happens with electron capture. Notice that the mass numbers stay the same, okay? 81 and 81. But what happens with an electron capture is that you take a proton, that's 36.
Neutrinos.
Above it.
That neutrino at the end right there?
He literally said
Both of
Neutrino?
these are 81. Those are your mass numbers.
Burkent, does that say neutrino?
Yes.
What's the element?
So,
Okay.
that's
Alright.
bromine.
Krypton goes to bromine.
So what happens that,
Okay,
and this happens exceptionally rarely, you have to bombard a nucleus with very high energy electron. So basically what happens is that you get an interaction, you bombard it with an electron. And again, to make the charge balance out, you have a positive proton that interacts with a negatively charged electron. So the overall charge remains the same. But what happens is that you decrease the proton count by 1. But the total mass number stays the same. So you've also created a neutron out of it. So basically what happens is you take a proton, you have it interact with an electron, it turns it into a neutron. That's why the mass number stays the same. That's why the atomic number goes down. But you have to make the total thing balance with charge. That's why you kick out a neutrino. So that slight difference in mass is carried off by the neutrino. So how we know this happens is that, again, you would start with krypton. You bombard it with electrons, what you would see is an increase in the amount of bromine in the sample. But you'd also be able to detect neutrinos that are being kicked out. Now, this is how this plays out. Let's say that you have a radioactive source, okay? And it can kick out different types of particles. And we're going to put a magnetic field out here.
Oh god.
X.
End of the
This
page.
seems like a
No.
question that would be on
This is on the desk.
Wait, why is there one O?
it. It seems like a
Yeah.
question.
Polymeric glasses.
Hell no.
Oh, you better remember.
Okay.
your answers, bro.
So actually, let me redo one of these.
Uh-oh.
Wait, why is there one O?
Review from like a unit ago?
No, those are all X's.
Oh.
Oh, all X's. Why is that one an O?
There's a
It's
mistake.
not,
Okay.
bro. Not.
So you have three options. One is a gamma ray that's been kicked out. One is an alpha particle, and one is an electron. Those are your three paths that you would see going through the cloud chamber. Which one is which and why?
That's a good
Oh,
question.
the third one's going straight.
Is electron the downward?
Why?
Because a proton would go up in that magnetic field, so an electron would go up. So it's moving to the
Left hand rule.
Okay, do the right hand rule.
Left hand rule.
Right hand rule. You're going this way. Which
Yes.
direction is the magnetic field?
Inward.
Inward. Which direction do the fingers point?
Oh,
So, this particle that goes up, is that the alpha particle or the electron? That's your alpha particle. Why?
Because positive charge.
Positively charged. So this is going to be your alpha particle. Now there's also something subtle about this. Notice that that is a pretty relatively shallow curve. So what do you know about the mass of an alpha particle versus the mass of an electron?
bigger? Small.
An alpha particle is much more massive than an electron. Okay? So it has a lot more inertia.
Oh.
So it's harder to get those alpha particles to get deflected because they have so much more mass.
Oh.
Now, if you use the left-hand rule, particles going this way, magnetic field is going in, your finger's going down. So this would be the electron. Notice that that curve is much more steep because it has less mass, so it's easy, less inertia, it's easier to get that to go through. Which particle is just going straight through? The alpha particle. The gamma, that gamma ray. Okay?
Oh, it's the
Because
gamma
it's
one?
just a photon, so it doesn't interact with anything.
Oh.
Okay, so here's, just hold on, Louise. So this is not, quote, an assignment, but here's what you have for this. So I've got everything worked
I
out,
think it's
okay?
the first,
This is literally the answer key to all of these problems.
but
And a lot of this is the binding energy, types of decay. So, this is Wednesday.
What's on the test?
Bro.
wait, it's Wednesday?
Never mind.
Hey, he's about to graduate.
Are we sure?
Are
we sure?
Let me graduate.
No, he's coming back for one more.
So we're review tomorrow,
Get those presents.
last test on Friday. All right,